Section 3.4, frequency response of underdamped systems. So we just showed in the last equations that for large value of t, the transient response is going to die out, and we're just going to be left with the steady state response, which is in and of itself a solution to the equation. So again, the steady state response is x of p of t is equal to x cosine of omega t minus phi p. And that is our steady state response. We know how to get x from f naught omega n omega and phi p, but let's go ahead and write it down just so we have it on the same page. So we've got capital X is equal to our mass normalized forcing amplitude multiplied by a long square root of omega n squared minus omega squared, that whole term squared, plus 2 zeta omega n omega, that whole term squared. And P is equal to tangent negative 1 of 2 zeta omega n omega over omega n squared minus omega squared. And we're just going to leave all that transient stuff behind. We don't need it anymore, right? We're just looking at the steady state. We're just thinking about t's moved down the road far enough that the transient doesn't matter. We're just focused on the steady state. All right. We want a way to plot this, because really what matters is not these equations, but it's the ratio of our natural frequency to our forcing frequency, right? Because if we excite a system at our forcing frequency, we're going to get resonance. We're going to get a very big response. So let's define a new term that we're going to call R, and that's omega over omega n. R is a pretty common term for this parameter. Sometimes you will get beta used at this, but we're going to use R. So if you're following along with another book, you might see beta, but we'll use R. So from this, and recalling that x, or let's just say this. So let's say, recalling that f naught is equal to capital F naught over m. And if we want to factor out some omega n squared from our x term before, so we have this x term up here. Let's factor out some omega n squares and put back in our capital F naught. We can get this expression, which is capital X is equal to, still a long division, F naught over m of omega n squared square root of 1 minus, a better square root sign, of 1 minus omega over omega n squared. And that whole term is going to be squared. That matches up with that parenthesis there. Plus 2 zeta omega over omega n. And this whole parameter here is squared. And again, we're looking to build up our ratio in terms of R. So we can rewrite this as F naught over m divided by, that looks much better, 1 minus r squared, that whole term squared, plus 2 zeta r, and that whole term squared. Okay. So, again, r is the parameter that we care about here because it's the relationship of our forcing frequency over our natural frequency.
Where did the omega clear? Like it was outside of the square root in the first part. Where did it go? Second.
Oh, it gets split and half of it comes to f naught over k. Thank you. That's where that goes. Good catch. Yes, f naught over k is pretty important to this. Okay, so we get our frequency. We can rearrange a few things to capital X of k over f naught, which gets us to a normalized parameter that we can put on the left of our plots that's coming up. Another way to talk about this is capital X of omega n squared over f naught. And what's left, if you move those things over, is 1 over the square root of 1 minus r squared squared plus 2 zeta r squared. So in a similar term, in a similar way, we can get our phase to be as a function of r also, right? So we can develop theta of p, again, we're only interested in our particular solution here, is equal to the inverse tangent of 2 zeta r over 1 minus r squared. So what I can do is I can take a table and I can say, let's build out a table of, a bunch of r values, maybe 0, 0.25, 0.5, 0.75, 1, 1.25, 1.5, 1.75, and 2. Right? And I could take a bunch of zeta values. Zeta, let's go zeta equals 0.1. So for a very underdamped case, add a little bit more. Zeta equals 0.25, zeta equals 0.5, and zeta equals 0.7. We still want it underdamped because we still want things that vibrate. And I can go ahead for all of these. I can get a value, right? A value for xk over f naught. So I can solve that at several different places. We won't do it in a table here. What we will do is draw out a plot and a few representative cases. But essentially what we're doing is if you were to fill out this table, you'll get a plot like this. And it's a lot of fun to draw it out because you can try to get in conceptual understanding of what our system is doing. All right, so there's my X and Y axis. On my Y axis, this is going to be frequency ratio, and it's going to be centered at 1. Why is it centered at 1? Because 1 is where omega n is equal to omega, which is where our system is going to be in resonance. If it's going to be unsolvable, or it's going to be undefined if there's no damping in the system, right? And so then let's backtrack. Well, let's say 0 and 2. So 0, 0.25, 0.5, 0.75, 1.5, 1.75, 1.25. And then on my left-hand side, I'm going to have my normalized amplitude. And that's going to be in units of x times k over capital F subscript 0. And I guess I didn't do a very good job here. This is in units of R. Maybe you want to put brackets around it so it looks more like a professional plot. Okay, let's say I have a very underdamped case. So let's pick our first color. Let's go with pink. And let's say I've got zeta is equal to 0.1. Because I have an underdamped case, these normalized amplitudes, it's sort of an arbitrary unit. I'm going to have a very high case of resonance, right? It's going to resonate a lot because I don't have a lot of damping in it. And this is what it will typically look like. It will start at a value of 1 because everything on this plot is going to start at 1. It's going to come up and it's going to dive down to about 0.5. And everything ends up about at 0.5. So if I add more damping to my system, let's go blue, and let's go equal to 0.5. So I'm a pretty damped case. I'm actually going to have something that looks like something like that, right? That works pretty well, but actually maybe let's put one in between. Let's try a green. So zeta is equal to 0.25. And this one's going to have a peak of something like this. Now, if I actually look through all three of these cases, I have a peak value here, I have a peak value here, and I have a peak value here. Let's just pretend this peak value is a bit to the left to solve my case. You're going to get a line that you can superimpose that goes up to infinity and more or less comes back like this. And this is your your R peak. Now, we don't have any undamped case here, right? If we did have an undamped case, let's say that we have I don't know if we can throw one in, but zeta it's equal to 0.0, right? So if we have an undamped case, our system would look a lot like this and a lot like that. And those lines would never match, right? Because your system is in resonance, right? With no damping, you have no solution. With no solution, there is no peak. You just keep tracking it for infinity. Okay, so this is what a damped case looks like. The natural question says, well, what if I have a critically damped case? If you have a critically damped case, the peak moves all the way here to the left on the red line. So if you have zeta equals 1, this is actually your peak right out here. And it looks like that. And you say, oh, that's fun. What if I had more damping, right? It's like dirt biking. More throttle is always the answer. So our last color, orange here, for zeta is equal to 2, it will look something like this. Right? And what you don't get is an oscillation. You don't get a resonance. You don't get a peak, right? It actually has the greatest peak at R equals 0. And again, because R is your the ratio, right, of your forcing over your natural function. So it gets the greatest peak when you just push something constantly. If you have a very stiff system, right, if you just push it, that's when it gets the greatest displacement. And as soon as you start to oscillate, that displacement comes back and back and back. If you have an underdamped system and you start to oscillate it, you can get some good displacement, like a swing or like a spring that you're shaking a little bit, right? But if you've got a rod in your hand and you're trying to get a lot of displacement and it's very stiff, you get the most displacement by simply moving it. The vibrations itself aren't adding displacement to your system. Okay, we have a beautiful picture here. Gorgeous. Do we see how close it is to the one done by code? I'm just kind of curious. You know, conceptually, it's close. So there is our conceptual plot that we kind of redrew. You have an R peak location that goes up the middle. You've got high damping greater than zeta is 1. And then you have a special case, which is 1 over the square root of 2, which we will talk about. Which we haven't talked about, I guess. Actually, I was completely wrong before. I apologize. Okay, so it does not change over at zeta equals 1. It changes over at the special function of zeta is equal to 1 over the square root of 2 is your change over point, where your max value is at 0. Sorry for that mistake. So when you have zeta equals 1 over the square root of 2, at this point, your maximum value here is at 0. So when you're at zeta over 1, your maximum value is at 0, but it's not the changeover point. The changeover point is this red line. So anything that's to this side of the red line will have a peak somewhere to the right of 0. And anything that's to this side of that red dashed line will have a peak somewhere to the left of 0. So the phase lag is also important, but not super critical in the context of a vibrations class, right? So you can plot out your phase lag for your system, and it will look like this. Typically, we don't talk about it too much in vibrations because we're mainly interested about the amplitude, which is what destroys things. And unless you have a very complicated system where you're trying to control movement of things in real time, like active vibration control or active damping mitigation, then you don't typically care about your phase. But this is what your phase lag will look like on that same plot for R over your phase in degrees. It is shifted up by pi for plotting, and that's just to get you a nice clean plot. Otherwise, it shifts down by 1 pi because you have that undefined number at a frequency of 1, right? So that's why there's that little shifted up by pi. If you ever want to plot one out, you'll see that you have to shift it up by pi to get a plot to line up. Okay, so let's think a little bit about where your maximum peak is going to be for all of these systems, right? We drew that line. We drew the line in your amplitude, but how do you know that the peak is here, right? How do you know that this is your peak? Well, it's relatively simple. It's just when our derivative with respect to r of capital X k over f naught is equal to 0, we're at a flat line, right? That's when I've got a flat line at the top. So with that, I can easily show that, let's just put that equation back in. 1 over, oh wait, I still want to do this, over the square root of 1 minus r squared plus 2 zeta r squared d over dr is equal to 0. And if I solve that out, I just get r peak, which is my maximum value, is equal to the square root of 1 minus 2 zeta squared, which is also, some people write as omega peak over omega n, right? It's in resonance at r equals 1, but because of your damping, your peak may not actually be at resonance. It may be slightly to the left as well. It will never be to the right of resonance. It might be slightly to the left of the resonance. But again, that is only true when zeta is less than 1 over the square root of 2. And that's very, very important. That's kind of a common exam question, is what is r peak? And then make sure you would write, well, it's the square root of 1 over 1 minus 2 zeta squared, but that's only true when zeta is less than 1 over the square root of 2. Because what's the peak when it's more? It's 1, right? It's just all the way, it's 0. It's r peak is 1. The value is 1, and it's at r equals 0. So we can rearrange this a little bit. If you want to find your peak value at your frequency, you could say that omega peak is equal to omega n, so your natural frequency of your system, times r peak. Let me put that in subscript. Nope, that's not what I want. So r peak. In case you want to find the omega that your peak system is oscillating at, right? So with that gives you a way to understand the steady state response of your system during a base excitation.